All right, so let's go ahead and get started. I'd like to welcome everyone to this seminar, and today we have a special speaker today. It's Azadeh Ansari. She is an associate professor at Georgia Tech and in the school, what is it, the School of Electrical and Computer Engineering.
Yep.
And she got her MS and PhDs in electrical engineering. Electrical engineering, computer science.
Yeah.
Yeah. So it's computer science from the University of Michigan, Ann Arbor in 2013 and 2016. Prior to joining Georgia Tech, she was a postdoc at Caltech in the physics department, and she's won quite a few awards. I'll start naming them right now. So, recipient of the 2023 IEEE Transducers Early Career Award. If you were at the Transducers Conference in 2020, you saw her receive that. She gave a nice little speech there at the same time there too. She got the 2021 Roger Webb Outstanding Junior Faculty Award from Georgia Tech. Usually those are for great teaching. So she's probably going to give a great seminar for us right now. The 2020 NSF Career Award and the 2017 ProQuest Distinguished Dissertation Award from the University of Michigan. Is that the best dissertation award at Michigan? Yeah, it is. Wow. Okay. As well as the 2016 University of Michigan Richard and Eleanor Towner Prize for Outstanding Research. So her research focuses on resonant MEMS, acoustics, micromachine integrated sensors, and microrobotics, all, I guess, the best stuff you can do, I guess, in my opinion. And so she's going to speak to us today about MEMS for next generation radio frequency biomedical applications. And so, Azadeh, take it away.
Thank you very much for the kind introduction. The pressure is on now after this. Thank you everyone for attending this seminar, and thank you for inviting me. Today I'll be talking about RF MEMS for next generation wireless devices and biomedical applications. So let me start by showing you the outline of the talk. So I'll start by talking a little bit about acoustic signal processing at RF. So the motivation behind having MEMS devices for RF in the RF front ends, and how can we add tuning and switching capabilities and adding ferroelectric properties to our acoustic resonators, and how do we scale the frequencies of these acoustic resonators to millimeter waves? So, going well beyond the traditional sub 3 gigahertz acoustic filters that we have in our cell phones right now. And then I'll talk a little bit about integration of MEMS sensors with electronics for having your sensors and transistors basically very intimately integrated on the same chip, specifically for pressure sensing applications at high temperatures. And then I'll talk about how can we leverage some of the nonlinearities in MEMS resonators in order to build higher sensitivity sensors and more, novel ways of sensing any sort of basically perturbation in the system. In the second half of the talk, we'll focus on the microrobotics. I'm going to come back to this outline in the second half. All right, so let's start with acoustic signal processing at RF. So this is just to motivate you why it's important to have a high performance filter. We know that basically the RF spectrum is getting more and more crowded, and it's important to be able to filter out basically the signal of interest in the presence of all of these out-of-band signals. So for this, you basically need a high performance filter. The metrics that people really care about is the insertion loss, the bandwidth, right? The selectivity, out-of-band rejection, and so on and so forth. So I want to basically justify why acoustics is a very good selection for filtering at RF. So the most important reason is that the acoustic, or the sound velocity in solids, is roughly 10,000 times smaller than the velocity of electromagnetic waves. So you can see that for any given frequency, the lateral wavelength, or the dimension of your device, which is proportional to the wavelength, is going to be 4 orders of magnitude smaller than the electromagnetic counterparts. So that basically gives you a lot more compactness for your filter design. Some of the state-of-the-art filter technologies such as magnetic or LC filters, empath filters using active elements, or evanescent cavity filters. These technologies are all great. However, none of them offers the small footprint, the low loss, because again, we're talking about mechanical Q factors, right? This is a lot higher than, for example, what you can get with your passives. Inductors, capacitors usually have a lot lower quality factors in tens of gigahertz range. And then most importantly, the passive operation. So this is very important again, because you can get higher linearities and lower power consumptions compared to the active counterparts. So this is the justification on why, acoustic filtering can be, very helpful at the RF front end. Now, let me just very quickly go over the principle of operation of piezoelectric resonators, which are the building blocks of a filter. So if you sandwich a thin piezoelectric layer between two electrodes and you apply an electrical signal between the basically top and the bottom electrode, you can convert electrical energy to mechanical energy and vice versa using a piezoelectric material. Some of the materials that have been traditionally used, very widely used basically, are quartz, that are used widely for timekeeping, lithium niobate, lithium tantalate, and more recently, aluminum nitride family. So what do we care about in resonators? So this here, you can see a mode shape. It's a thickness extensional mode of this a resonator structure that you can see here. And if the frequency of the AC signal that you're applying here matches the resonance frequency, the mechanical resonance frequency of the structure, basically you get a very sharp peak in the impedance or admittance response of your resonator. So here again, the input is electrical, the output is electrical, but basically the signal processing where this resonance is happening in the mechanical domain, and that allows you to get higher quality factors than you normally can with electronics. Now, the metrics of these resonators, which are the building blocks of our filters, one is obviously the resonance frequency. How high is it? How high can we push it to be? And then the coupling coefficient, which has to do with the piezoelectric properties of your material. So there's always this quest for going after materials with higher and higher coupling coefficients. This coupling coefficient will define the filter bandwidth, as we will see later. And then the quality factor, which is inversely proportional to the loss in your resonator, or how, showing as how steep or how sharp basically this peak is. So once we have these building blocks, what we care about it is this figure of merit, which is Q times the KT square, the effective electromechanical coupling coefficient. We can basically put these resonators together in different configuration, coupling it mechanically, electrically, or even using maybe passives. But one of the very traditional ways that these have been used, especially for cellular applications, is electrically coupling series and shunt resonators with slightly shifted frequencies in what is called a ladder type filter to build, a nice, basically a high figure of merit filter. All right, so having said that, let's take a look at a typical RF front-end module and see where these filters are located. So again, like right after the antenna, it's very important to have a very low noise filter, because this is the most critical stage in terms of keeping the signal integrity and not adding noise to the signal. So here you can see basically these filters that you probably have more than 40 of them right now in your cell phone that use acoustic technology. Some of the industry or key players in industry for building these type of filters is for Bob, Skyworks and Broadcom, for Saab, Murata, and Corvo also. So basically these are the key players in the bulk acoustic wave, BAW, and surface acoustic wave filters. Now, these frequencies, again, have been traditionally limited to below 3 gigahertz. Now, what I want to emphasize here is that, again, we know that the RF spectrum is becoming more and more crowded. There's more exponential growth in the 5G, 6G market. There is also need for compact filters for defense applications, such as in active electronically scanned arrays that have large bandwidth and can, can cover this 2 to 18 gigahertz range. So basically, with all of these motivations, we're looking in how can we scale up the frequencies of these filters, and how, by material innovations, resonator optimization, and then different filter topologies. So I'll try to cover these three areas in the first section of this talk. So the first part is adding scandium to aluminum nitride, which is a widely used material for RF MEMS. Again, it has been super popular because of the versatility in the deposition or growth. Right? Sputtering aluminum nitride can be low temperature, so it can be deposited post CMOS, usually gives you high Q. You can also use epitaxial aluminum nitride, which can be compatible with 3-5 semiconductor technologies such as MEMS or aluminum nitride, gallium nitride, all the 3 nitride family electronics. Now, in the recent years, basically, scandium has been added to aluminum nitride lattice. And people have observed that the piezoelectricity can actually increase by 5 times as you increase more and more scandium into the aluminum nitride lattice. So this was basically shown in 2009, that the piezoelectrically increases. And the reason for that is that basically the word-side crystalline structure of aluminum nitride starts changing in this C-axis to the A, basically lattice constant proportion changes and the piezoelectricity increases. Now, more recently in 2019, for the first time, it was shown that you can actually switch the polarization of aluminum scandium nitride, let's say from metal polar to nitrogen polar. So this was it was very important, basically, to see these very nice white box-like polarization versus electric field profiles, which adds switching capability to your otherwise purely piezoelectric material. So basically, there's been a lot of interest in this aluminum scandium nitride material because the piezoelectric effect is higher, the electromechanical coupling goes higher, and you can build wider bandwidth filters, and you can also use the switching or tuning for frequency tuning in your filter. So my group has used multiple materials basically to build AlScan resonators and capacitors. So here I'm just showing that basically with the 1 micron thick aluminum scandium nitride, you can observe this very nice box-like structure, and that you can also tune this coercive field by changing the temperature of the environment. So as the temperature goes on, you need less of a barrier energy to basically switch the polarization from, let's say, aluminum polar to nitrogen polar, and you can by 3x basically lower your coercive field. Generally, the coercive fields in nitride ferroelectrics are very high, so you need to apply a lot of voltage in order to switch the polarity. So this was the first demonstration of the temperature dependence of these coercive fields in the ferroelectric metal capacitors. Now we went on and built FBARs, or film bulk acoustic resonators, which are these thickness extensional resonators that I showed before, using these ferroelectric materials. So here you can see basically the SEM images of 2 types of FBARs, one that is released by releasing a silicon, and the silicon device layer on an SOI substrate, and the other one which is released from the backside by using the bulk of the silicon. And we were able to show that you can basically tune the polarization of your FBAR and effectively turn it on and off by playing with the voltage that you apply, the DC voltage that you apply to the AlScan layer. And this work also reported the highest KT square for FBARs, about 19%. which again just means that this enables wider bandwidth filters, and that's something that a filter designer would really like to have. Now, let me tell you a little bit about how can we scale up the frequencies, right? Again, traditionally, sub 3 gigahertz FBARs have been very widely used. However, how do we go from 3 to 18 gigahertz, right? That's the question. Can acoustics basically handle this much of a higher frequency? So one easy way is scaling down the thickness of your piezo layer, because again, we know that the frequency is inversely proportional to the thickness of your resonator in a thickness extensional resonance mode, right? So we're going from a film that is about 1.11 to 1.2 microns to a piezo stack that is about a 200 nanometer thickness, right? So this is not basically a simple thickness scaling solution. There's a lot that happens when these thicknesses are, scaled down. So all the wavelengths basically become comparable in size to all these non-idealities in your material, such as the surface roughness, the grain boundaries, the size of the grain boundaries become important. And then you also have to thin down the metal layers, right? Not just the piezo layer. So how do we thin down our metals without increasing the sheet resistance? And how do we deal with stress and breaking of the devices, power handling, dielectric losses, and so on and so forth. So for this, basically, we partnered with two groups, one with University of Michigan, which are MBE growers of 3-nitride materials, and with the goal to build very thin layers of aluminum scandium nitride grown on a molybdenum bottom electrode, and then released again through the silicon substrate. So here we're showing that very good material properties could be achieved, and that the sheet resistance of the epitaxially grown moly, this was done at IQE, which is a semiconductor manufacturing company. So we could basically measure sheet resistances comparable to bulk molybdenum, because we were using actually single crystalline epitaxial moly as opposed to sputtered moly. Now with this, we optimized the F-bar for having a high KT square, and we were able to fabricate two types of F-bars. One is that they're in single F-bars and series connected or cascaded F-bar, which each of the F-bars are matched to 25 ohms instead of 50 ohms, so you can increase the area and therefore get a larger KT square. So this work was published in Electron Device Letters and was featured as the editor's top pick, where we were showing a very nice, 18 gigahertz peak, very clean, no spurs around it, with a high KT square of about 10%. So this is one of the highest, basically, F-bar devices made of aluminum nitride family in literature. However, as you can see, the quality factor is about 150, which could be better, and I'll try to explain, what we've been looking into and how can we improve the Q above this number. All right, so let me just show you some of the trends in the Q, KT square, and thermal conductivity of aluminum scandium nitride materials. So as I explained, the nice thing about this has been that the KT square increases a lot just because the D33 goes up, right? However, if you look through literature, and this is work by a lot of research groups, not just us, is that the Q of the resonators, as the scandium composition is increasing, is decreasing, decreasing with increase in the scandium concentration. So we became curious, is that a fundamental reason? Is it just that the material is not very mature yet, or there are, non-idealities in the growth, or what is the reason for this, continuous drop? Another thing that we measured was the thermal conductivity of scandium aluminum nitride, and we realized that basically as the scandium is increasing, there's a 30x drop in the thermal conductivity, which means that the self-heating becomes a lot more severe in aluminum scandium nitride FBARs, right, compared to aluminum nitride. Especially for 5G applications, we know that there's more and more powers that needs to be dumped into these resonators, and this temperature can actually go up a lot if we are using ALSCAN in terms of aluminum nitride. So my group is interested in basically all these material properties of aluminum scandium nitride and these trends, these challenges, that come with adding more and more bandwidth to your filter. And another thing that we have been looking into is basically the intrinsic phonon-phonon losses in aluminum nitride and aluminum scandium nitride materials. So if you take a look at the Akizer and the Landau-Rumer limits, which are basically, again, intrinsic phonon-phonon losses in these material systems, you will see that basically all the reported data is a lot lower than what the theory suggests, right? So basically, we're interested in looking at the fundamental limits in disordered thin films, especially when the film gets thinner and thinner, right? A lot of factors play a role in adding more scattering losses in acoustic materials and devices. I mentioned a few of them. For example, the grain boundary size become different. The thickness itself plays an important role. And in the case of aluminum scandium nitride, we have this alloy scattering and the alloy scattering that is added due to the mass difference and the strain difference when introducing scandium in your aluminum nitride lattice. So this is something that I think the entire field still lacks to have basically some more realistic Q estimations based on all the non-idealities or the specific material properties in the thin films. Now, let me conclude this section. So I showed some ferroelectric aluminum scandium nitrides, which were the first of their kind with highest KT squared to date. And basically showed you, high figure of merit FBARs. However, as we saw, the Q can still be improved. It's not close to the material limit. It can be a lot higher. So some of the basically solutions to improve the Q is adding multi-layer stacks where the polarization can be periodically switched. So if you add up and down layers with polarization up, polarization down layers, you can actually excite higher order modes without losing the coupling. So this is basically one way that a lot of groups are actually looking for scaling up the frequencies without losing the Q and the KT square. And another way is basically, using a thicker layer stack, such as a silicon or silicon carbide, that can improve the quality factor of your resonator. It'll degrade the KT square, but the Q times KT square is what matters, right? The figure of merit. So you can basically add more peaks by having a composite structure. This will help with the Q, it'll help with the self-heating, and it can basically enable multiple peaks that you can switch between for building, switchable filters or covering a wider range of frequencies. Now, let me move a little bit and talk about how can we integrate MEMS and electronics. And of course, there are many ways for doing this. Well, one thing that our group was recently funded was this DARPA HOTS program that wants to build 800°C pressure sensors, where the sensor and the transistors are all intimately integrated. So I showed that aluminum nitride is a very popular material for MEMS, but or something that hasn't been really studied that well is how aluminum nitride can be a good material for very high temperature applications. Again, it's a semiconductor that has an ultra-wide band gap, 6 electron volt at room temperature. It's a word-side crystalline structure. It's got a large thermal conductivity. It's very stable. And more recently, there has been a lot of work on doping aluminum nitride. So that enables building aluminum nitride-based electronics. So our solution for this integrated pressure sensor and transistor is having an aluminum nitride thin film, which is your MEMS, on an aluminum nitride substrate, which holds the electronics. right? So the idea here is building an oscillator with a resonant pressure sensor and aluminum nitride electronics. And you can think that there are, many ways to basically integrate your electronics, whether it's with aluminum nitride or CMOS, with the MEMS. Some of the things that I showed earlier all had a sacrificial layer or even the silicon layer, which was etched with xenon difluoride to create these suspended membranes. But here I want to show you how we can actually use flip chip bonding to bond the MEMS die to the aluminum nitride substrate, or to any substrate, basically. We are choosing aluminum nitride because we care a lot about coefficient of thermal expansion, CTE. Due to the very high temperatures, it's important to have both of these layers be of the same kind. Otherwise, the thermally induced stress will just peel off the MEMS part. So I'm going to show you a way that basically you can just bond with either metal layers or other materials to bond the MEMS die, which is sputtered aluminum nitride on silicon, to your aluminum nitride electronics, and then etch away the silicon to form this, air cavities or these suspended membranes. So just a quick show of what we have done so far. So we have our basically MEMS die on the top, the silicon is removed. So you can see the aluminum nitride, the moly, and then this cavity, which for this particular pressure sensor is very important for us to have a defined cavity depth. Because the way that the pressure sensor works is a little different than static pressure sensors and even, damping-based resonant pressure sensors. So here what happens is that when the pressure in the environment changes while your membrane is resonating, the gas that is trapped in this very thin cavity will exert a force, which basically modulates the stiffness of the membrane, and therefore your resonant frequency shifts. So as the pressure is going up, the frequency is actually increasing. So your membrane is stiffening instead of softening at higher pressure levels. And this can allow you to actually read out the pressure outside with a high sensitivity using this frequency shift detection method. And the substrate on the left-hand side, you can see that you have your aluminum nitride substrate, and this is the MEMS die where the silicon is removed. So there are 8 pressure sensors, right, all on the MEMS chip that are flip chip bonded with, better than a micron resolution to your substrate. So this is the work in progress. We have only tested these up to 350 degrees C. We're looking forward to higher temperature measurements, which is, when things get more complicated. Now, maybe move on I talked about frequency detection sensors, or FM, frequency modulating sensors, where we take a look at the frequency shift when there's a perturbation in the environment, in this case, a change in the pressure. Now, I talked about also scaling down the thickness of these piezoelectric layers from traditional 1 to 2 microns to sub 500 nanometer. Now, when you look at this membrane resonators, where basically this thing is like a drumhead resonator. I don't think the video is not playing, but basically it just moves up and down like a drumhead. And when the thicknesses become thinner and thinner, there is what we call Duffing nonlinearity that increases, which shows us a bifurcation in the frequency response. What this means is that the geometrical nonlinearities kick in at lower power levels, at lower input power levels, as your transducer becomes thinner and thinner. And you can see these basically non-symmetrical resonance modes with bifurcated frequencies. Now, a lot of times you want to stay away from these nonlinearities. However, you can also, embrace it and leverage these nonlinearities that show up, in your basically harmonic oscillator equation, and see how can we use these to build more interesting sensors, all right? So that basically brings me to frequency combs or frequency comb generators. So we know that in the optical domain or optomechanical frequency combs have really revolutionized spectroscopy, optical communications. They got the Nobel Prize in 2005, and they're generated basically, as you can see here, with a lot of, oops, sorry. Back. Right here. So we have what we call frequency teeth, right, with a set spacing between each of these two teeth, and phase coherence between all of these signal lines, right? And again, many different methods have been used in the past, using mode like lasers, electro-optical modulation, four-wave mixing, microresonators that use Kerr nonlinearity. Now, in the mechanical domain, the question is, can we use Duffing nonlinearities and modal coupling between different phonon modes to try to replicate this kind of a frequency comb in the optical domain? And the question is, yes, we can. And in fact, let me give you a brief history of fully mechanical frequency combs. So the first one was only theoretically predicted in 2014, right? Where the idea was basically using a drive frequency at the sum of two phonon modes, so omega I plus omega j. And if you solve the FPU chain equations, this basically a PRL paper showed that theoretically you can see what looks like a comb. It's not symmetric and it's very finely spaced, but it clearly resembles a comb. And then later in 2016, out of University of Cambridge, and 2018 in my group, we were able to observe similar combs experimentally in our MEMS resonators or NEMS resonators. So 2016, basically what you can see here is that used two resonance mode that had a 1-to-2 commensurate basically relationship. So one resonance mode was sitting 2x of the frequency of the other. And when pumped at this 2x frequency, a comb like this would appear, right, at this other resonance mode and also at this one. Now, what my group worked on was non-degenerate parametric pumping, in the sense that we have two resonance mode and you can pump at the sum of these two frequencies. And we were able to show frequency combs where the spacing is actually tunable. So you can change your pump frequency and amplitude and be able to create tunable spacing frequency combs, as you can see here. And then later, we also worked on other ways to pump, and we were able to observe harmonics of these combs sitting at frequencies as high as 40 megahertz. Again, you can see that all of these mechanical work are at a lot lower frequency than the optical counterparts. But after that, there has been a lot of work more recently on various ways to excite combs. And for example, here in 2022, you can see a 1-to-1 pumping where they claim you don't even need coupling. And under very certain conditions, and there is what they call a negative friction, that you can actually create a comb just by pumping at the resonance mode. There's a lot of work with internal coupling, internal resonance coupling, so 1-to-2, 1-to-3 pumping, and so on and so forth, that recently there has been a lot of interest in. Now you may ask, the bandwidth aren't, the way that with optical combs they can expand in octaves. Here you have narrower bandwidth, and it's more of a new field, so the application isn't very clear. So things that we have looked at for application of these frequency comb, one is for ultra sensitive sensors. Now, what do I mean by that? For example, infrared sensing is one big application that basically just relies on changing the temperature of this resonator and being able to see the frequency shift due to the temperature difference. Now, if you use this non-degenerate parametric pumping platform where you pump at the sum of these two mechanical modes, when the temperature changes, you can actually engineer the temperature coefficient of frequency for each of these modes to be different than what your material sets these TCF values to be. For example, here you can see that as the temperature is increasing, one of the modes reduces in frequency while the other increases. And then the next thing is, how can we use combs for this kind of a temperature sensing platform? So let me just show you with these kind of frequency combs, you can see what are called the Arnold tongues, meaning there are certain areas in terms of the pump frequency and amplitude that combs exist. You have to basically just have the very right condition to see a comb. You may not see anything. It's the blue area, right? You may see just a signal and an idler, like what I showed here, or you may see the full comb, or you may see this kind of a triangular envelope, more noisy signal, right? So I showed TCF engineering for this area where you only have a signal and an idler sitting close to your resonance modes. But if you take a look at the combs themselves, you can see that as the temperature, for example, is increasing, these are measurement results, the spacing between these combs are increasing. So instead of looking at the frequency shifts of your mode, you can actually take a look at the change in the spacing of these comb teeth. And you can read out a lot higher TCF values, giant TCF values, if you look at the change in the spacing divided by the spacing itself. And the two, the two farthest teeth from each other also show an n times larger frequency shift if n is the number of your frequency fingers or teeth. So these are just some of the applications. Obviously, this area is a little newer and open to other applications and understanding exactly what's happening, being able to predict where do the combs happen, how can we design for them. Now, let me shift gears very quickly, I don't have much time, and talk a little bit about microrobotics research area. So as I mentioned, I talked a lot about piezoelectrics and resonance, but like how can we actually use resonance and where we know how to excite very well, right, to make things move. So this work basically includes a PZT, piezoelectric, actuator. And then we 3D print using a two-photon lithography, two-photon polymerization, or a TPP technique to 3D print a polymer base where the piezo material is sitting on top. Now, what we do is that when you look at this oscillation of your piezo, right, that induces a stick and slip motion in the legs of your robot. So we showed that basically by just actuating either the PZT on top or a piezo shaker on the bottom, right, you can make this robot move, right? So what we were interested in was, can we have controllable motion, or is there any dependency on the motion with the frequency at which we're actuating? Can we design different types of legs, right, with different diameters, different angles, and be able to control the robots, address them individually within a swarm? So we started 3D printing different robot legs, right? Here in this video, you can see that depending on the angle of the tilt of the legs, some of them actually move a lot better than the other, right? So there's clearly a dependency on the geometry of these robot legs. So we started doing console simulations to see, are we hitting any resonance mode of the robot itself? And I want to emphasize, a lot of work has focused on individually controlling the legs of these robots, but here it's just the monolithic design. So instead of, individually controlling the legs, we're just applying one frequency and hoping that the resonance mode will do the selection for us. We were able to clearly see that at specific frequencies, the speed of the robot peaks, right? Which corresponded with these eigen modes of the robot in the stick mode. So this was basically just a very simple actuation, unlike the bulky magnetic counterparts or unlike having single actuators for different legs, and with a, CMOS compatibility prospect, right? Because again, like you can have simpler aluminum nitride, aluminum scandium nitride, even PZT, and integrated with other ways to build these kind of legs in this monolithic approach. And this work was basically received a lot of pop media attention. There was like, sorry, Wally, this is now the cutest robot. And this is covered also in Nature Electronics, just because of the simple, actuation and the fact that you can tune into the resonant frequency of each robot to make it move. So it gives it addressability, capability within a swarm. then we started looking into if we can actually sweep the frequency and see if different kind of motions can be generated. And we were able to see two very clear regions where we see forward motion and backward motion as the frequency shifts. Those videos are slow, but you can see basically we are applying the same frequency, just sweeping the voltage, and the sky starts to move backward, while at another frequency, which corresponds to this region, you can see that the robot moves forward. We also see that these forward and backward regions are dependent on the tilt of the legs very, very clearly. We did some dry friction modeling. Actually, the modeling also shows that you see a clear forward and backward region, and that there's this angle dependency as well. So we started thinking, can we design robots that have two sets of left and right legs that have different geometries, and you excite only one set of leg, then you excite the other set of leg, and you're able to steer the robot left and right, right? So this one is slightly bigger. Again, that the TPP method takes a long time and it's quite expensive. So for prototyping, we went on with more regular 3D printers. So these are not as scaled down as the previous ones that I showed you. And we're actuating the PZT on top with a piece of wire. So the signal generator is external to this. But we're basically sweeping the frequency and showing that the robot is able to move in all the principal directions, right, as the frequency is shifting. Now, what we did next is that we started combining or superimposing two sine waves, right? So we knew, for example, forward is 49 kilohertz, backward is 62, 103, 96 kilohertz. And then you can obviously superimpose two sine waves and be able to cover the entire 2D space. I think that video was fast, but here, yeah, so you can play with the weight of the signals that you're applying and basically, cover the entire 2D space this way. So then, we thought about what about swarms, micro bristlebot swarms. So this work is in collaboration with a roboticist who used to be in our school at Georgia Tech, now is at UC Irvine. So this one, again, is not using the fanciest 3D printer. So you can see that the legs are a little coarse, but the idea was, let's live with the non-idealities and see if we can still develop algorithms that can help. I'm going to move really fast because I'm running out of time here. So basically, the idea here was use physical models, so the friction collision between the robots, and still by changing the global conditions, which is the amplitude and frequency of the shaker beneath these robots, can you have stable clusters or can you have more dispersion, right? So where we never actually form a cluster. And then we use this to build a closed loop experiment, a bang basically controller, where we monitor a metric which we called MIPS index, and we can we can have clusters and then dispersion by playing with the global field input amplitude and frequency. Now these could be scaled down. The idea is, can you scale these down, use it for cell manipulation, lysing. We know we can 3D print blades, we can 3D print, whatever you like basically on these robots. And these are, again, with TPP, so these are very small. We're using a small magnet underneath basically to move these guys, again, with stick and slip. So here I'm just showing that we were able to put, we printed little blades, and when we applied a DC magnetic field, this only has a thin layer of nickel on top. So under basically a sawtooth waveform underneath the stage, the robot is doing stick and slip, moving forward and backward. And then once we apply a DC field, the tip gets engaged and it can puncture, in this case, just a leaf. So right now it's basically, now the DC gets applied and the robot is, on demand, basically tilting to align with the magnetic field, and it can engage its tip. All skip, this is a collaboration work with JPL, where we're just building sensors for underwater exploration. So multiple sensors to be mounted on the robots for, practical swarm application for underwater exploration in the icy moons of, the planet. Let me talk a little bit about the biomedical applications in a few minutes that I have remaining. So the idea here is that there was a neurosurgeon that basically came to me from Emory, and she said basically every time that they do surgery to access deep-seated tumors, there's a lot of functional loss to the patient and a lot of healthy tissue that gets destroyed to access, different regions, and they're really in need of a tool that can do nonlinear trajectories, right? And the idea was, can we use microrobotics for these kind of a neurosurgical, minimally invasive applications? So what we showed was that you can buy a 250 micron magnet and then 3D print using 2-photon polymerization a drill bit, right, on top of this magnet, which basically this is made of a resin, and it can be built on top of the little magnet that we have here. And then we use a Helmholtz coil, so XYZ coils that you can see here. I'm a grad student basically manually wound. And when you apply, it's quite a low magnetic field, 10 millitesla rotational field, with a joystick, you can actually control this driller to drill inside of an agar gel. So again, this is not swimmers. Swimmers have been a lot more worked on. It's a lot easier to move in a fluid. This is actually puncturing a gel that has similar mechanical properties to the brain. They actually use this as a mimic of the brain tissue, and he's trying to basically write GT. You can still see that there's a lot more control, closed loop control, that needs to be done for a more precise manipulation, but this was still pretty cool in the sense that you can go from air into the gel, and that the speed is controllable with frequency. Again, all of these give you a lot of control if you want to do swarms or individually address these robots. And then what we did next is that we added a hydrogel that can have drug in it. And in this case, we just put fluorescent dye. And depending on the pH value of the environment, the hydrogel can swell a lot more, for example, if your material is more acidic or if the environment is more acidic. And the reason for this is that tumors tend to have a different pH value than healthy cells. Therefore, if you have a selective, basically, hydrogel that releases the drug or the dye at different pH values, this is 6.2 versus 7.8, that's really good for on-demand or more like local drug delivery. So here again, you can see this work. This was featured in PBS, Your Fantastic Mind, actually in September. So it's quite recent. You can take a look at this. This is 250 microns in diameter and about a millimeter in length. And with that, let me just conclude here. So the holistic approach, I just talked about the fab, and basically drug delivery a little bit, but there's a lot more into this to take it to the point that actually we get FDA approval and it can be used in patients. You have to think about imaging. That's the most important part, right? And being able to track it, the control, and so on and so forth. So here you can see some of the items that we have to be aware of when designing these tiny machines. It's not just about fabricating them. And then, thinking about what kind of imaging modality would be best for real-time imaging of these devices until, they're really trained. How do you know the XYZ or can localize these, with precisions that are required for neurosurgery? So to conclude, basically, I talked about in the last part some of the neurosurgical microrobots. I talked about how you can add a pH-sensitive drug delivery approach and co-developing a coil system that is compatible. In our case, we're we're building a CT scan or a coil system that is compatible with a CT scan for real-time imaging. And the idea would be, can we add more and more MEMS sensors, on a very, very miniaturized platform and be able to do, in vivo testing. With that, let me acknowledge all the funding sponsors, all my students, past and present, who really did all the work, and I'm just here presenting what they've done, and the collaborators. And thank you all for hosting me at UC Berkeley. Thank you.
All right, thanks very much, Azadeh. Questions for Azadeh? There you go.
Why do you want to so the question, what's the disease like? What's the
So
can you repeat the question?
yes,
For people
yes.
online?
So the question is, why should we have a pH-sensitive hydrogel for drug delivery applications? And the answer is, it turns out that basically the tumorous cells are more acidic slightly than the healthy cells. So when the robot moves to the to the location that you really want the drug to be locally released, if your hydrogel is sensitive and swells more in the acidic region, it's going to release the drug faster when it hits the target.
I see. So the specific drug is going to
in the tissue, so it's basically
tissue.
yes.
So you are doing
Yes.
or just
It's in the tumor.
into a tumor?
Yes.
So maybe of this micro is mainly
Yes. Yes.
Okay, great. Another question in the back?
So I have a question about the
Hmm?
Can you go back to the slide?
Sure.
So that there's vision of the scandium a lower.
Yes.
So because we really have a product, right?
You have a what? Sorry.
So the AFQ product
Uh-huh.
is advanced materials. So how would the frequency change?
So generally, as you add more and more scandium to the lattice, your lattice becomes softer. That's another reason why you can easily switch it up and down, right? So the frequency decreases slightly as you add more and more scandium. I didn't put this here. All of your basically your CIJ matrix, it gets lower, so the frequency decreases slightly though. Yeah, but you can account for that by changing the thickness or the pitch of your resonator. Yeah, so the F does decrease, the Q also decrease. The only thing that goes up is the KT square or the coupling.
Okay.
Yeah.
The next question is about the frequency.
Uh-huh.
Are you keeping
So that's a great question. So you're asking if the temperature is going to swing or if the temperature is constant. Yes. Yes. So basically, yeah, I'll tell you, the requirement for this DARPA project is that we're at 800 C and it's not changing at all. However, if the temperature also changes, there are a couple of ways that you can, account for that. One is to have a reference oscillator, right, that doesn't move with pressure, but only moves with temperature. So you can calibrate out the impact of the change in the temperature in your frequency shift. Or you can try to design, maybe it's a little harder, resonators that have more of a flat TCF response at around the temperature of interest, right? So that you don't get as much of a swing in the frequency when your temperature is changing, and you get more of that when your pressure is. You want to have a pressure sensor, not a temperature sensor, right? So you either calibrate out using a separate one, choose so you build two and you look at the differential frequency shift, or even one, but like use two modes. And also, generally just try to minimize the TCF around the temperature of interest. Yeah, but that's a great point. I mean, any resonator kind of senses everything, so you have to be smart enough in which parameter you want to.
Okay, so the question here and then there. You go first. You go first.
It's also kind of a question about the same topic. So I was curious when you choose bonding the integration.
Yeah, that's a great material, great question. So we're using platinum for now. And platinum is pretty stable at high temperatures, and we're using metal bonding. And there are other things that you can use. For example, you can use ALD zinc oxide and anneal it, make sure that basically at high temperatures the bonding is stable. But for now, platinum is what we have been using for. High, yeah, very thin layer.
Thermal compression bonding?
Yes.
Why not gold?
We did use gold also. We were a little, so again, we haven't done the 800 C temperatures yet because we're still waiting for the measurement setup. It's not a easy one. We were a little worried that gold wouldn't be as stable at higher temperatures as platinum. With our just, pads, we observed that platinum is a better material for 800 degrees C. Yeah, but we have gold as well. We'll see which one survives better. Yeah.
Okay. So Will?
For the RF resolution project with the aluminum nitride, as you mentioned that there's a trend that with even though you get like better, I'm wondering the decrease of the Q factor attributed to I mean one thing I would say is this two parameters just contradict? No, because you have a more natural that coupling with
lower Q.
Or
yeah. That's a great question also. So generally Q times KT square is a figure of merit, and even within the same material system, right? Usually if one goes up, the other one compensates. So however, what I am trying to talk about here is that this Q drop is not only because of your coupling going up, it's because of the scattering mechanisms that are added to your aluminum nitride lattice when you add scandium, right? So the exact, the exact modeling, I would say, is actually a subject of future work, but we know that now you have a ternary alloy, so there's more scattering from the phonon alloy scattering, right? We know that a lot of times actually the crystallinity of the film becomes worse as you increase scandium. Your thermal conductivity is changing. A lot of the material properties are changing. So there are fundamental reasons to have different Qs as you start increasing the scandium content. Yeah. So it's beyond the, it's beyond the Q times KT square kind of material limit. Yeah.
Do you also run into more spurious responses when the KT square goes up?
We don't, because we use very simple kind of just F bar structure. So our responses have been pretty clean with more scandium, but things that I know other people, for example, have observed is these, they call abnormally oriented grains. Like the surface isn't basically as smooth as when you have an aluminum nitride. That itself could be, again, another reason why the Qs tend to drop with aluminum scandium nitride. Yeah.
So we take one more question, then we have to head for the restaurant because they close at a certain time. Did I kill the question because I said that? I may have done that. Yeah, I think I killed the question. All right. Well, yeah. All right. Well, thanks very much. Thank you, Azadeh.
Thank you.